This is the first session on the appendix in the textbook. Appendix A, the one-dimensional infinite array of delta wells. It's the Kronig penny model. Showed you this last session. Parts of it are from, I'd say, well, definitely graduate level, M1, M2 level, which just gets thrown at you by the text as well. Particularly something called the Bloch, B-L-O-C-H, Bloch's theorem. That just gets thrown at you. I can make it try to sound fairly plausible, but the actual proof that this works, I mean, it's a theorem, right? You have to actually prove it. But that's rather advanced stuff. So you know, beyond undergrad level. So anyway, we can still do quite a bit, and some homework involved as well. We need to do a bit of algebra. The algebra is not so hard. The hard part is Bloch's theorem. All right. Now, setting the scene a bit. What are we trying to do? We mentioned before, so a bit of revision. We're moving on from 3 delta wells to 4, and we don't actually do it, but a pattern starts emerging when you go to 5 or 6 delta wells. You notice certain periodicity, a certain periodic pattern is emerging, and that's where Bloch's theorem comes in. It explicitly puts in this periodicity into the algebra that gets used for describing the wave functions that are solutions to your n delta well problem. Right? Now, in a sort of hand-wavy way, this will become a bit clearer later on once we've done the math. But again, I ran out of board. You probably have heard me say that a lot, and I'm becoming increasingly conscious of it. And remember, this whole experiment is, well, just that, it's an experiment. It's an ongoing experiment. I'm more than seriously thinking. I may even tomorrow go to the guy from whom I bought this board. He has contacts with a company that manufactures them, and I will ask him to make me a bigger board so that I can just write more stuff up and have longer sessions. You know, just when it gets interesting, I have to cut out because I've run out of board, which is upsets the intellectual flow. Okay, so anyway, in a hand-wavy way, what comes out of all this analysis when you have n, you know, and n goes to infinity, n delta wells, we're talking the one-dimensional case, so you just have these periodic spikes, you know, separated by distance b, little b. Imagine there's sort of like, I don't know what the word is, teeth, like in a comb, you know, spikes in a comb for your hair. So just imagine an infinitely long comb and these spikes, you know, these coming up periodically. And when you do the quantum mechanics for that system, when you have n, you know, n is large, number of delta wells, the bound energies, you know, the wave functions, the allowed states, they tend to bunch up into bands, like. If that's the energy level, then you'll sort of get a band of allowed energy levels, and then a blank, you know, another band where no energy levels are allowed, you know, a disallowed region or band, and then you get another band opens up where you can have allowed states, allowed energies, and so on. So you get sort of allowed band, forbidden band, allowed band, and so on. And that phenomenon, it's that phenomenon that makes the use of transistors possible, right? These forbidden regions and allowed regions, or bands, as they call it. They're just like if energies that way, you get you know, between energy level so much and so much. Though in between those sort of that energy band is allowed, that kind of thing. and this comes out of the analysis of 1D array, so of delta wells, right? So so we've done it for 3 in the previous session. Now, if you go through the same kind of analysis, the boundary conditions, continuity, normalization, blah blah blah. If you do the same sort of thing for 4 wells, so here are the positions of your 4 wells, you will get 4 possible allowed states, allowed wave functions, allowed eigenfunctions, allowed eigenvalues. In other words, they're all the same. They're all 1-to-1, right? So with 4 wells, n is 4, you get 4 possible states. And again, because the potential is symmetric, the wave functions, from the parity theorem, the wave functions are either odd or even. And you've got 4 of them now, so these 2 are even functions, and these 2 are obviously odd functions. Now, if you keep doing that, like for n is 5 and n is 6, you'll notice certain periodicity. Like here you're starting to see it, right? It's sort of repeating every, I don't know, I guess a wavelength. I guess you'd call that a wavelength equivalent, or the period in x. This wavelength, if you like. And if you did like 6, then you'd have three of these and whatever. So a certain periodicity is emerging, and as your n increases, this periodicity becomes more and more obvious. So I guess, well, I'm not quite sure who pioneered this sort of work. I don't think it was Bloch. I think his work was more on other things. But once you become conscious, as your n increases, that you're getting a periodic, that your eigenstates, your wave functions, if you like, take on this sort of periodic behavior. It would be nice to have the mathematics itself, the algebra that you're using, reflect this reality, this periodic reality. So that's what's attempted in this appendix. Now, remember, it's an appendix, right? So appendices are used usually for what purpose? Well, I guess 2 main ones. One is for some topic that's slightly at a tangent to the main theme of the chapters, so it's put in as a kind of extra. Another reason, there's probably lots of reasons, but for appendices, but another major one is when something which is considered important but maybe a little too difficult for the general level of the text, and I think that's the case for this appendix, because there's stuff here just thrown at you. All right, so the motivation now is to try to find a better formula. Now, in the previous session, we had a formula for S. Remember, S was just a separation. It was some factor times little b, and little b is the distance between the wells. Okay? So, and this S, this separation, was a function of eta, and eta was some factor times the energy, the allowed energy of the wave functions for what we did for three delta wells, right? So we're looking for a better formula for S, for the separation. That's a function of your eta. Now I gave you again, it was a bit thrown at a formula, or 2 formulas for the even parity case and the odd parity case, and they involve natural logarithms, L of n, that sort of thing. So we want a better formula than the one given for the 3 delta well case, right? So to motivate the Bloch theorem use, to show its applicability, now remember, between each delta well, your wave function u will satisfy this st. Oh, it was my computer, not my. I just had a little panic there. I heard a ding. That was the computer, not my camera. Because I really think now I've solved the memory problem, the memory allocation problem. Okay, so the wave function u between the delta wells will satisfy this st of this form, right? So your u will decay exponentially, right? Now, so the idea now is, and to analyze this fully requires a higher level of analysis than is suitable for undergrad. But anyway, in a sort of hand-wavy way, make it sound plausible for you. So now the usual solution for the wave function here is just of this form, right? Now we've seen that several times, so that's okay. So we've got a 1 here. That's for just one delta well, and this equation would let's see, sort of, yeah, it lies outside the well, the infinitely thin well. So it's of that form. All right. So let's try to modify this somewhat. So there's a certain periodicity. Every, like if you had 6, if you had n equals 6, you had 6 delta wells, you'd get I don't know, you'd get 1, 2, 3, I suppose, 1, 2, 3, yeah, this sort of thing, and you notice that there's a periodic pattern emerging. So now admittedly this is just thrown at you, right? This comes from Bloch's theorem, and the textbook doesn't state what that is. It's just this is consistent with Bloch's theorem, which is a rather famous result in advanced quantum mechanics. So don't worry about it too much. Just accept it. Okay. So this is the equivalent of this, but it's built into the math that it has a certain periodicity. Now this is your solution. This is your wave function between two neighbouring, important neighbouring delta wells, right? So your x here, remember this whole analysis is in one dimension.